Okay, minor technical difficulties. All right, so this is Discrete Mathematics. This is I'm Scott Grizzard from the University of South Florida. I'm supposed to say these things before I start up the lecture. And this is Discrete Mathematics. Today we are going to talk about Cantor's proof that the real numbers are uncountable. So let me address some of the questions about not Discord, let me address some of these questions that have been popping up in Discord chat. Okay, so question, when will I post the study guide? I wanted to have it finished yesterday. Hopefully it will be finished tonight, and I'll have it up for you. I promise by tomorrow it will be done. Hopefully it will be done tonight. I have not written the test yet. I've got an idea of what I want on the test, and I will talk about the test at length on Wednesday. Next question, stuff about the Proctoria. Okay, so Proctorio doesn't accuse you of cheating. Proctorio flags suspicious behavior, and I check. Now, are you allowed to pull out your phones and check and scan your pages? The answer is absolutely. So what will happen is Proctorio will flag you, but it will flag you at the very end. Okay, so when I look at the videos, please remember to put your shirts on. When I look at all the videos, I'll look at where the flag is. And if the flag is, and the other thing it does is it compares your flags with everybody else's. So if everybody else has a flag 2 minutes before they end the quiz, the thing goes, it's probably something that's supposed to happen. Okay? And remember, it doesn't accuse you of cheating. It just simply says there's something you might want to look at. And it's got this consistency thing. So the thing that it flags, if you care, is the way the algorithm works is it flags things that other people aren't doing. So if everybody at around the same time looks down their page at the same thing, okay? Oh, there's a question on whether or not the audio is working. Oh, okay. So the person who's saying they can't hear, refresh your browser. Often that fixes problems on Twitch. Let me kick the cat out of here. Okay, he's gone. She. All right, so the audio appears to be working. The thing that it does, nope, cat's gone. The thing that it does is that the system flags abnormal behavior and it says, hey, look at this. So absolutely, you can use your phones to do the scanning. That's also the part, if you want to do scanning, you're supposed to hold up your notes to the camera first and then scan them. The reason why is that if there's any suspicious behavior, we can check them. I have not been checking every single person's Proctorio videos for quizzes. I will be checking them all for tests. What I've been doing for quizzes is checking like 1 out of every 3 or 4 or 5. For tests, they will all get checked, but for right now, I'm not really doing everybody's. So if you've been cheating and I haven't caught you yet, you got away with it, but you won't get away with it on the test because and I haven't reviewed all the videos yet that I'm going to review on the quizzes anyway. So I'm sorry I can't show the cat. The cat's gone now. Any questions about that stuff? Okay, so 1 to 5, how do we feel about this whole Proctorio experience? Not that we like it, it's kind of creepy, but 1 to 5, how do we feel about 1 to 5, how do we feel about Proctorio? Just making it work. Not how much do we like it, how confident are we that we can make it work? For the test. And then if there are issues, again, I'm going to run you, we're going to do a bunch of stuff on Wednesday, but I don't want Proctorio to be the thing you're stressed out about it when it comes to take the test. So is it cheating? Remember that the quizzes are given before, but they're supposed to be closed book. So it's just like it was before, where the quizzes are supposed to be closed book, and you take the quiz, and you have the quiz ahead of time, you look at it, then you put it away, and then you show your area to be clear, and then you take the quiz closed book. And I hope that I was clear about that. If I was not clear about that, then get very clear about that, because they are supposed to be closed book things. Are there any other questions? Okay. So that's Proctorio. There's going to be a lot of questions about Proctorio. For the test, what you're going to do is you're going to have a stack of, notebook paper. There's notebook paper. You'll have a stack of notebook paper in front of you, right? So what you're going to do, you have a small stack, hopefully. What you're going to do is you're going to take the notebook paper, you're going to go, see, it's blank. Then, see, it's blank, right? When the thing tells you to. Then at the end, you're going to say, okay, this was this page, this was this page, this was this page. Now, the test is online. So all you're going to have are like 2-3 pages of scratch paper to show me, okay, at the end. And then what you're going to do is you're going to scan your scratch paper and upload it to Gradescope, right? And you did this ahead of time, so I know whether or not the scratch paper matches what you uploaded. Okay, so you're going to show blank paper at the beginning, you're going to show the rest of your thing, and then you're going to show the thing. And again, I don't want you stressed out about Proctorio, okay? I have to do something to ensure the integrity of the test, okay? But I don't want that to be the thing that stresses you out, all right? Are there any other questions about that? And this seems to be a stressful issue, so on Wednesday, I'll go through the entire process, okay? I'll make a special presentation on Proctorio and exactly what you're going to do. Are there any other questions? Okay, study guide, again, I'm going to try to get it up tonight. This evening, I've got like meeting, but hopefully somewhere in between after those meetings, or probably during the meetings, because the meetings will be boring, I will be posting the study guide. So the procedures, yes, so the procedures, hopefully not. It was frustrating, the mounted camera, hopefully not. I think the procedures are pretty tight. I know it's kind of frustrated to like hold the camera and go up, down, left, right. So yeah, I understand that. There are options though. I mean, I've got the different mounts. So, are there any other questions about that? I don't want to spend the time talking about the Proctorio. So let's talk about the quiz. Okay, so the quiz. And I mean, and then if you really want to know what the study guide is going to look like, what is the study guide going to look like, guys? You've done enough of these. The study guide's going to say, oh, study your quizzes. And then it'll have specific ones. Yes, so that's my plan for the study guide. Study your quizzes. But of course, it'll be a little bit more than that because I'll tell you the specific quizzes and stuff to expect. The structure, it's going to be a mix of short answer, multiple choice, a few true false ones, and then a couple of the quizzes, a couple of the test questions from last time, which I'll give you. I'll tell you which ones I'm going to change and which ones, if I give them to you, I will give you verbatim, and stuff like that. So it'll be stuff, that I thought was really important from the last section that you didn't quite understand. There'll be a lot of clockwork and arithmetic stuff, and I'll tell you, as usual, I'll tell you what all you can expect. Okay, so if there are no other questions about that, let's go ahead and talk about the. Let's go ahead and talk about the quiz. Oops. Okay. So the quiz. Oops. I want this up. Sorry. Sorry. The backup plan DocuCam is giving me trouble, but it's the backup plan, so hopefully we'll need it. Quiz is graded out of 10. Yada 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 yada. So compute this thing. Right? Any trouble with this? So I start at 0. I go 2 to the 0. And 2 to the 1, 2 to the 2, 2 to the 3. So this is 1 plus 2 plus 4 plus 8 equals 15. Okay, 1 to 5. How do we feel about that process? my 1 to 5er seems a little slow on the 1 to 5ing. He's probably still in a meeting. Okay. So we feel pretty good. Okay, the symbol Q. There we go. All right. The symbol Q representing the rational numbers. How do we feel about that one? It's just the rational numbers. And then let's put them both together. So this is questions 2 and 3 together. That these two, this one represents the rational numbers, this one represents the integers. Okay. Now, when I'm submitting my quiz, of course, this one was a text box. This one was a text box, and then these were multiple choice problems. Okay? So if I wanted to justify what I was saying on a multiple choice, I'd write some kind of justification here. And I'd write some kind of justification here, and I could write a little work here. So the format of the test is going to look kind of like this. Online, and justifications are purely optional, right? They're for partial credit if you feel like it. Okay? So online, I would write, this is this, and this is this, and that's that, and I would just send it off. Of course, this one, there's not much to say. And then the questions, part of the test gets auto-graded. So these would all get auto-graded, and then one of the TAs or one of the graders would come back in and look at your, questions you missed, they'd look at your stuff on GradeScope and say, oh, this question, you had some reasoning here. We'll give you half a point for it. Again, purely optional. You don't have to turn in any scratch work if you don't want to. Okay. Now this one, if p and n are both positive integers, then n to the p minus 1, mod p equals 1. That's false. And the reason why that's false is because I didn't make any demands on p and n. So if I take 4 to the 2 minus 1 mod 2, well, that's 4 to the first mod 2, which is just 0. Now, if I want to make it formats, I would have to say that p must be prime and p does not divide n. Okay, or n mod p does not equal 0. This would make it true but it's false right now because, I haven't made those conditions. How do we feel about that 1 to 5? Okay. So I've got the conditions. Again, those are kind of little tricky things. I think Michael may have lag. All right. The next one here is that accountable. If there exists a one-to-one relationship. Now, this is something I'm going to talk about because I found out you guys were asking me some questions about this one-to-one business. And if you look in the textbook, there's actually 2 definitions for one-to-one. So I'm actually going to talk about that right now. But right now, this is true. A one-to-one correspondence or one-to-one relationships. Okay? Michael, don't worry about it. I'll take care of the 1 to 5s if you could answer questions in chat. So I'm going to talk about this today. And the 2 different, remember there's a math definition and there's a computer science definition. And I want to talk about that today because that was actually leading to some people having confusion versus the textbook. Because the textbook uses both as well. So what I'm going to do is I'm going to clarify that. So how do we feel about that one? Okay. I apologize for the lag. It's because of the time. It's basically at 3:30 in the afternoon is peak time. It works, in the morning, there's no lag. The people that are watching in Colombia are, able to do everything real time. At 3 in the afternoon, so at 9 in the morning, it's fine. At 3:30 in the afternoon, it's laggy. So there's nothing I can do about it. That's why. I don't know if it's laggy. It's what's the word I'm looking for? Anyway, it's not low latency or whatever that is. Okay, so the rational numbers are countable. We did last time the proof that's in the book that the rational numbers, that the positive rational numbers were countable. And that proof is on page 477 in your textbook, section 7.4. So, and we also did that the integers were countable. Okay? So now what we want to do is we want to talk about this idea. The question is are the rational numbers, the positive rationals, are countable? And remember that countable meant that I have this relationship, this tight relationship with the natural numbers. Okay? So the way I showed that this is, remember I had this one for the rational numbers, which I called S0. So let's let T0 be negative S0, right? So on S0, I had 1 over 1. And so T0 is going to be negative 1 over 1. S1 is positive 1/2, and T1 is negative 1/2. And so on and so on and so forth. Now, if I start at 0, and then I go 0, U1, I'm sorry, 0, S0, T0, S1, T1, S2, T2, S3, T3, S4, T4, S5, T5, etc., etc. I can now list all of the rational numbers, both positive, negative, and the 0. Okay? So that's a little bit hard, but the idea was that I can, from the sequences I already had, I could build up a new one. The other way to think of it was that, well, let's see, the rational numbers are countable. That probably means the negative ones are too. And 0 wouldn't go in there, so you can do a bunch of other things. So how do we feel about that? Okay. Conceptually, that's a little bit harder. We're getting into this idea of infinity and infinity of being of a certain size. And there are things that are, this idea that the set of rational numbers is infinite. And there are an infinite number of rational numbers between the number 0 and 1. But they're the same size, these two sets. I've got an infinite number of rational numbers between 1 and 2. But in essence, there are just as many rational numbers as there are natural numbers. They're the same class of infinity. Okay? And that's weird. Okay? But the importance is that I can loop over these things. Okay? There's some way to set it up so that I can loop over them. It's ugly, but there's some way to do it. Let's talk about the real numbers. The real numbers are different. The real numbers don't have a way to loop over it. And that's the point of today's thing. So in order to get at this, so 1 to 5, by the way, how do we feel about the whole quiz? Okay, so given the numbers in chat that people are posting, I think I have about 30 live viewers from my class. My question is, who are these other people? Okay, so there's trouble. People are having issues with 4C. That was this idea that I start with 0, right? So here's my list of the positive rationals. Here's my list of the negative rationals. Okay? And what I want is all the positive rationals and all the negative rationals and 0 in a list. Okay? An ordered list. I need some way to create an ordered list. Okay? So I'm going to start at 0, and then I'm going to pick the positive one and then the negative one. Then the positive one and then the negative one. And then the positive one and then the negative one. And then the positive one and the negative one. And so on and so forth. Until what I wind up with is a list that includes 0 and an infinite list that includes 0 and then every single rational number. In other words, if you give me any rational number at all, there's some point in time that I will get to that rational number. It may take the age of the universe and longer, but at some point, I would loop over that number. I would consider that number. Okay? And that's a very tough concept. But what's really weird is the fact that I can't do that for the real numbers. I can do it for the rational numbers, but I cannot do that for the real numbers. And that's just freaky. Okay? And that's what we're going to talk about. So we're already kind of freaky. And now we're going to do more freaky. So let's talk about that. I want to do some cleanup first. And I need to clean up this idea of one-to-one for math versus one-to-one for computers. So I'm going to talk about that, the computer term versus the math term. And then I'm going to talk about the fact that I'm going to do a little bit of calculus. The very second lecture in calculus. The first lecture I already given calculus is the one you've already seen about functions. I do it a little bit more formally, but that's the first lecture from calculus. The second lecture of calculus is about the limits of sequences. And that's what we're going to talk about at first today, because I need one concept that's not in the book. And the book kind of goes, yeah, don't worry about it. There's this kind of bit in here where you need the fact that repeating decimal forms are not unique, but repeating decimal forms are unique. So I'm going to get into this idea that there's two different decimal forms for some numbers. Okay. So you just have to step carefully when you do this proof. And then after that, we're going to do Cantor's diagonalization theorem, which is the one in 7.4.2 on page 479 is where it begins. Okay, and we're going to do the proof just out of the book. All right. And it's very nice. And the reason why we're going to do it is because it's kind of a slick way to get at a lot of these kind of computational things. This is the first one. The first big one is that there's things I can't even enumerate to. All right. Are there any questions before we begin? Okay. So I had this question in, someone emailed me this question because they were confused about this thing called one-to-one and onto. So one-to-one and onto, there's both a math definition of one-to-one and a computer definition of one-to-one. So let's deal with this. It's this minor little detail, but it needs to be dealt with. Okay? So a function, remember f is a function if every x gets used and no x is used more than once. F is one-to-one if no y is used more than once in math terms, okay? But I can miss y's. That's fine. I don't hit them. But that's okay for this definition. Okay, missing y's. So for an example of this, let's consider the function here. Let's consider the function x goes to 2x where these things are natural numbers, right? So my x space is the natural numbers, my y space is the natural numbers, and I take this function where I map 1 to, 1 should go to 2. I apparently cannot do simple subtraction. Okay, so we'll fix it that way. So 1 maps to 1, 2 maps to 3, 3 maps to 5, 4 maps to 7, and so on and so on and so forth. And I miss 2, 4, 6. I miss all the even numbers, right? I'm only hitting the odd numbers. However, I never hit a number more than once. And that's the idea in math terms of 1 to 1. So how do we feel about that, the math term 1 to 1 in math? 1 to 5, how do we feel about that one? Okay. All right. So that would be an example here. This is also called an injection in mathematical terms. And I'm no longer going to use the word. So the left side are the X numbers, the Y side are the Y numbers. That's a good question. I should have labeled that. So there's X and there's Y. Okay. And I take X, whatever my X is, and I map it. This is an alternate way of saying and I'm only doing it for the natural numbers. Okay. And the idea is that I don't hit all of the Y values, but I never hit one more than once. Okay. Now, this idea right here, a function is called onto if every Y value gets hit. Now, I can hit a Y value more than once. That's okay. Okay? The functions, the X cannot be repeated. That's correct. But here the X is not repeated. Okay? Here the X is 1, 2, 3, 4, 5. And my Y's are 1, 3, 5, 7, etc. But I can use Y values more than once in a function. And I can't if it's 1 to 1. 1 to 1 says I can't use Y values more than once. I can't use X values for just a function. I have to use every X, but not, and I can't use an X more than once. And now I'm adding the condition that I can't use a Y more than once. Okay, which is okay. These are just extra conditions. Okay. But here I want to talk about what happens a function is called onto if every Y value is hit. But I can hit Y values more than once. So let's look at this function here. F goes from the natural numbers to the natural numbers, where X maps to 1 to X over 2 if X is even, and X maps to X plus 1 over 2 if X is odd. So that means that 1, which is odd, is going to map to 1 plus 1 over 2. 1. Right? 1 plus 1 over 2, which is 2 over 1, which is 1. Okay? Here, 2 is even, so it's going to be 2 over 2, which maps to 1. 3 maps to 2, 4 maps to 2. 5 is going to map to 3, and so is 6. 7 will map to 4, and so will 8, and so on and so forth. And the point is here that every Y value is going to get hit. Now, here, every Y value is getting hit more than once, which is okay. But it doesn't have to be that way. Okay? How do we feel about that process, 1 to 1? How do we feel about that process, 1 to 5? This idea of onto. Now, this is a mathematical definition. And in math terms, and if ever I want to use this term again, I'm going to use the term surjection. Okay? And the reason why I'm doing that is because I don't want to confuse the math terms and the I don't want to confuse the math terms and the computer term. Okay. Now, in math, if something is both an injection and a surjection, we call those things bijections. Okay? Or permutations, either one. Okay? But in math, if I have a circumstance where I hit every number, and I only hit every number once, we call that a bijection or a permutation. So here, I have this idea where this maps to this maps to this, I'm sorry, that maps to that, but that maps to that, and that maps to that. So every x value is only used once, every y value is only used once, but every x value is used and every y value gets used. Okay? Now, a correspondence or a relationship in computer speak is one-to-one if it is both injective and surjective. Okay? So what computer people call one-to-one is what math people call both one-to-one and onto. Okay? And I want this because the term is confusing in the book. So the book does the same thing where it confuses these two terms. Okay? How do we feel about that, 1 to 5? This idea between computer and the difference between the computer definition and the math definition. Okay. All right. It's a little confusing, but if you think about a database table, you think about everything in here having an index here. Okay? These tables, I run a join on these tables, and I wind up where everything is used. Now, I can have different relationships right? I could have relationships in a database that act more like a function. Okay? Where I don't use everything in the other space. But here I want to think about a tight space. I want to think about it, the ID for this one could be the ID for that one and nobody would care, right? Because they're really the same table. For some reason, I'm storing them separately. Probably has to do with storage and memory, or searchability. But I don't actually care. They're really the same thing. Okay? All right. So I want to stick to the computer terms, and I don't want to spend too much time getting lost in this. And if you have questions about this, I'll be happy to do it. And somebody was asking me about test questions. You'll see the type of question that I'll ask about this on the quiz for Wednesday. Because it's pretty much the only question I could ask for the quiz on Wednesday. Think multiple choice or true false. Okay. And I'm going to do my best not to confuse the terms. I'm going to do my best to use, when I'm talking about one-to-one, I'm going to use this term for one-to-one. If I want to talk about functions in a math sense, I'm going to use this term here or this term here. So the terms here that I will use, I'll even highlight them, are, thank you. The terms that I will use in class are this one, this one, this one, but only for computers. And then this one if I want to talk about things in math. Okay? But when I talk about one-to-one, I mean bijection. And when I talk about bijection, I mean one-to-one. Okay? So I want to keep to the computer terms, not the math term. I don't want to use this term. I don't want to use the math definition for. I don't want to say one-to-one and mean math. Okay. Are we on board with that? 1 to 5. Exactly what I mean when I say 1-to-1. So injection means every Y is used only once, and surjective means every Y gets hit. Okay. So you're very close. The fact that every X gets used is just a property of the thing being functions. And the fact that every X only gets used once is just a property of functions. Okay. So let's talk about something that's even more confusing. Okay. Let's talk about repeating decimals. And this is a calculus aside. If you are interested in this stuff, I will be teaching calculus apparently next semester at 9:30. If you want to take calculus, I'll be happy to do it. Just to let you know, I'm a little bit less laid back in calculus than I have here. Calculus, we have a big thing that you have to get through, and here we had a short thing you had to get through, and then, I got to pick topics after that. Let's talk about this. And again, this is not in the book. What do I mean by a decimal? A decimal is a decimal relationship, okay? So, no relationship, a decimal. What do I mean by a decimal? What is a decimal? It's actually a series, okay? A decimal is a series. Okay? It's something I sum. Okay? So let's consider the number 0.33. That is the sum as k equals 1 to 3 of 3 over 10 to the k, right? This sequence right here is 3 over 10 plus 3 over 100. Oops, I need another 3 there. Plus 3 over 1,000. Okay? Which equals 0.3 plus 0.03 plus 0.003, which equals 0.333. How do we feel about that? 1 to 5. Oops, not 53. Now I've got 3 on the brain. So all I'm doing is I'm saying, okay, what is a decimal expansion? Well, it's really 3/10 plus 3/100 plus 3/1000. And it terminates. So we call this a terminating decimal expansion, right? So this right here, this one terminates. Okay? Oops. Let's consider instead, let's consider one that doesn't terminate. So all terminating decimals can be represented like this. Okay, obviously a 3, it wouldn't be 3. This is a terminating sequence of 3s. But what happens if I keep going on forever? In other words, what is 0.33 bar? Okay? There's the question. What is that? What it is a sequence. It's the sequence 0.3, 0.333, 0.33, 0.333, 0.333, etc., etc., etc. Right? It's an infinite string of 3s. Is everyone on board with that? 1 to 5. How do we feel about the fact that what I have is an infinite string of 3s? Right? That's what the decimal means. 3 over 10 to the k. K started from 1 and then going to infinity. And I keep adding 3/10, 3/100, 3/1000, 3/10,000, 3, etc., 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 100,000, 3 1,000,000th. And I keep adding 3. And when I do this, I get a number called 1/3. Okay? Now, why do I get 1/3? Let's look at this here. So if I pull up my old crafty calculator here, okay, this is the sequence. I start at 1, and 1 is 0.3. 2 is 0.33. my 3 maps to 0.333. And then I keep going, correct? Here I've added, 13 decimals. At some point it stops adding decimals, right? It just goes, oh, that's 0.3333. But if I drew a line right here at 1/3, okay, this would approach 1/3 indefinitely. Okay, no matter how close I wanted to get to the number 1/3, there would be a term here that would get me that arbitrary distance. So give me an arbitrarily small number. Let's start with the number 0.0001. Is there a way for me to get 0.0001 away from 1/3 using this sequence? How far would I have to go in order to get closer than 0.001 to 1/3? Right. If I went 6 decimal places, I'd be there, right? How many ends would I need to go to get within 0.0001 of 1/3? And the answer is, well, 6 will definitely do it, okay? And right? So let's ask ourselves, what's the difference, right? What's the distance? So if I do this, I get 1/3 minus, let's see, you said 6 decimal places, right? So 3/1, 2, so 1, 2, 3, 4, 5, 6 decimal places. Okay? The common denominator here is going to be really, really big. Okay? Everyone on board with that? But this distance is going to be less, whatever it is. And as I said, the common denominator, I'm sorry, this should be 3, not 3, it should be 3, 2, 3, 4, 5, 6. There we go. And whatever the common denominator is, it's going to be very, very, very big. But when I'm done, I'm going to be less than 0 than 1 over 1, 2, 3, 4. I'm going to be less than that. Do I need another one there? Yes. Okay. How do I feel about that, 1 to 5? That I can get arbitrarily close to 3. I'm sorry, arbitrarily close to 1/3. So this idea, right? Any small number you give me, if you give me 1 billion, is there an n that will get me within 1/1000th of 1/3? Yeah. Is there an n that would get me within 1/1000th of 1/3? Well, yeah. If I go to n being a billion, I'm going to be within 1/1000th of 1/3. No, it doesn't have to be 6. It's not how many do I need. Okay. So how many n's would get me? It's not. And the point is that this is going to be a very, very small number. Okay. And I could probably use, I don't know, what would work? 4, 3. A 4 would definitely do it. 5. Okay, Michael's probably got the answer. So that's the idea. So this intuitive definition, okay, is that the limit of the sequence is the number that I get arbitrarily close to. Okay, that's this idea, this intuitive definition of a limit. And there is a formal definition of the limit that we could do, but but we're not going to. This idea of getting arbitrarily close to a number. But that begs the question: what about the sequence 0.9999999? Okay. What about the sequence 0.99999? What is it? So here, this idea of the repeating decimal, 0.33333 actually is 1/3. What is 0.9999999 repeating? What is the number I approach? Okay? And it's important to note that that number is the thing. Okay? So here, the limit as n goes to infinity of the sequence k equals 1 to n of 3/10 to the k is 1/3. And that's what it means for the decimal expansion to be 0.33 repeating. It really is that number. It's not something I'm approaching. It actually is that thing. That's how I define the 0.333 repeating. Well, now if I get infinite, if I take n's forever, I wind up at the number 1, which someone has said. And that's a little weird. Let's look at it. This right here was my sequence up, and said I'm going to do 9 here, and I'm going to zoom out. Yeah. Here's 0.9. Here's 0.99. Here's 0.999. Here's 0.99999. And I guess you're going to stop after that. Right? The computer's so close to 1, it's going to say it's 1. It's not actually 1 yet. Okay? But there you go, right? It's some arbitrarily, this number right here that number actually is 1, which means that decimal expansions are not unique. And that's something that's skipped over in the thing. Okay? What does the word arbitrarily mean? Arbitrarily means no matter how close you want me to get, right? Something's arbitrary. I can ask you to give me a distance, whatever insignificantly small distance you want. Okay? So you give me a distance. You give me 0.00001 away. Okay? I can get you that close to this using this sequence process. I can find you a sequence that is arbitrarily close. No matter how accurate you say I have to be, I can get you that accurate. Okay? 1 to 5, how do we feel about this concept arbitrary? What I mean by that? Okay. This is a tough concept, and it's not something that I'm all that concerned about you don't understand here. Take calculus, then we're going to talk about it some more. Okay? But this idea of arbitrary closeness, this idea in calculus and analysis or whatever. And it's one of the hardest ones it's one of the hardest definitions in calculus. It's so hard that most of us just kind of skim over it and go, arbitrary. And then we move on with life. Because calculus is a lot more than just this. But this is one of the subjects that you come back to in Calc 2 and then come back to again. And then you become a math major and you take analysis, and then they, hit you over the brick with all this stuff. But for the moment, just know that there's this idea that 0.99999 repeating actually equals 1. And decimal expansions aren't unique. Okay, enough of that. I just want that in the back of your mind. Don't get super lost over that. I'm basically throwing 3 very tough concepts at you at once and going, have fun. Okay. So decimal expansions are not unique. Well, the next thing I want to do is I want to prove that there's no way to list the real numbers. In other words, that there is a bigger infinity than just the infinity you're thinking of. There's a bigger infinity out there than the infinity of the natural numbers. Yeah, man. There's really big infinities. Let's talk about one. Let's talk about a really big infinity. Let's talk about R. It's really a theorem. Okay? So what I'm saying here is that there's a bigger infinity at play. And this proof here is by Cantor. And I should have his picture for you. Hold on. Let's put him there. This is a big result. Okay? The idea, hey, look, I'm good, Cantor. No. So the idea here is that there's things that are bigger. Okay? All right? So proof. Suppose otherwise. Suppose now, remember that the real numbers, I know, hi everybody that's rating us. Welcome to Discrete Math. We're going to prove that the real numbers are uncountable. Have fun. Okay, so in order to do this proof, I mean, people are really bored if they're going, oh, let's go watch Discrete Math class. I actually think this is really real proof. So if you want to stick around, this is kind of blowing mind things. Okay? But yeah, so I've got this idea that something is bigger than regular old infinity. There's something bigger than the natural numbers. And this proof is found on page 480 of your textbook. Okay? So let's do it. Suppose that there's some way for me to list them. Let's do it. Let's list them. All right? Suppose there's some way, well, let's look at our list. Let's look at the decimal expansions, and I want the unique decimal expansions. Right? And I want those expansions to be unique. So in order to get them to be unique, I'm going to choose the non-terminating forms, okay? So if there's a choice between a number like 1 equals 1.000000 and 1 equals 0.9999999, I'm going to choose the 0.9 version, okay? Because those are the only numbers that do that. The only numbers that can be represented two different ways are the ones with terminating forms, okay? So let's do them all without those terminating forms. Okay? Let's list them. I don't know what all they are, but I'm going to wind up with a list that looks something like this, right? I'm going to have 0.1, 1, 1, 2, 1, 4, 6, 8, 5, etc., etc., etc. I'm going to have 0.3145792217 dot dot dot. I'm going to have 0.867530901982. I'm going to have something like 0.587621872. I don't care. The point is that there was some way to do it, and there was an 80s joke in there somewhere, which was important. Now, I have a big list. However I list them, there's going to be some way to do it. Now, and this list is infinite. Now, this is called diagonalization, and it's extremely important for, it's kind of the way you prove all of these things that are weird. Okay? What I'm going to do is I'm going to choose the decimal expansion. I'm going to choose this term from the decimal expansion. And then I'm going to choose this term, 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 and then I'm going to choose this term. Right? And so on and so on and so forth. Okay? So I'm assuming that there is some way to list the real numbers. And I'm choosing from each of the decimal expansions, I'm choosing one of the numbers. There's no reason that that should be a different color. Which pen did I use to get that? I probably used this one. Okay. Now, for each one of these columns, I'm going to do this. I'm going to call dn equals 1 if A, how does he do it? Let me do his exact same indexing. In. Okay, so this term right here is A1, 1. This term here would be A1, 2 in his indexing and so on and so forth. Okay, so what I have here is I have this as index 1, 2, 3, 4, 5, 6, 7, 8. And then in his system, I'm also indexing the columns. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. So here I've got 9 columns, and I've got 8 rows. This is his scheme. And he's going to say, okay, 1 if A n n does not equal 1, and 2 if A n n equals 1. So what I'm going to do is I'm going to flip them. Okay? So here in this case, my new number dn equals 0. Now, ANN here, oops, wrong one. ANN here is 1. So according to my formula, that just became a 2. A22 is 1. So that just became a 2. A33 is a 7. So that just became a 1. A44 is 6. That just became a 1. A55 is 1. That just became a 2. A66 is 2. That becomes a 1. A77 is 2. That 4. That becomes a 1. And A88 is that. Okay? And I'm going to wind up with a number that is different from every number on my list. More to the point, I wind up with a non-terminating decimal that's not on my list. Now, what's the problem? I have a number that is at least 1 digit off that has at least 1 digit different from every other number at the list. Okay? But I assume I had listed them all. And that's a contradiction. In other words, R, the size of R, is bigger than the natural numbers. It's bigger than the rational numbers. Okay? R is big, really big. Remember what Douglas Adams said about space? Space is big, really big. Well, R is really, really, really big. Okay? It's a bigger infinity. Okay? it's bigger. Okay? The technical terms, I don't really care if you know them, but these are called Aleph numbers. We say that the size of n equals the size of q equals the size of z equals what we call Aleph naught. And I can't do an Aleph. It's, something like this with one of these, and then something like that, right? It's like this. Right? It's a Hebrew character called Aleph naught. I think that's about as good as I'm going to do. Okay? And then we call this thing right here, we call this the set R, the cardinality of the set R, and we call that Aleph 2. I'm sorry, Aleph 1. If you care. Don't need to know. And that's it. Right? Thus concludeth the stuff for test 3. Are there any questions? Oh, I know there've got to be questions. This thing's confusing. This thing's like big, cool. What? Okay. So what I assumed. Yeah, there it is. So what I assumed that I could list them. That's where that list of numbers comes. Okay? Suppose otherwise. Suppose there's some way to list the numbers. I don't care what they are, but just suppose there's some way. And then I made a list, right? Somewhere I have a list of these infinite number of numbers. And what numbers they are, I don't care. Okay? The fact is that I had an infinite list. Okay? I had some infinite list. And you'll see the same thing. I used a different infinite list than the book did. It doesn't matter. The point is that there's some infinite list. I don't care what it is. Okay? What I care about, though, is the fact that when I wrote the infinite list, I could construct a number that was non-terminating and that was different than every other number on that list. Okay? That's all I cared about. And because I could create it that was different than every other number on the list, then, the number that I was looking for wasn't on the list. Okay? This number that I created, I assumed that there was a way to list them, and then I found a number that was not. It was like the prime numbers. Remember, I assumed that there was a finite number of primes, and then I found a number that was either prime or could be divisible by a prime not on my list. I've done the exact same thing. I've created a list of all the numbers. Okay? An infinite list, mind you, not finite now, infinite list of all the numbers that are in the real numbers. And then if I change one digit, if I create a number that is one digit off from every single number on this list. And remember, this list is unique. Okay? The numbers on this list are unique. Because I'm excluding the finite. I'm excluding the terminating expansions. I'm using the non-terminating form of every number. I create an infinite decimal expansion that was not on my infinite list. Right? And yeah, it's weird. Note the dates on George Cantor. Okay? Look at his dates there. Okay? 1845 to 1918. Okay? This is some stuff here. This is not something that the ancient Greeks figured out. Okay? This is something that Cantor figured out. Okay? We're talking, 1870s type thing. 1880s. Okay? So what I found is a bigger infinity. And the point is that if I assume that the natural numbers exist, and then I make all these other things, if I start, constructing things with that set. I construct these rational numbers, and then I add all these sequences in by constructing real numbers. And I wind up with something that's bigger. Something that's bigger than the natural numbers. Okay? And that's the idea. That the cardinality of this thing is an infinity of a different order. It's bigger. And that's weird. But it proves something. It proves that I can't enumerate the real numbers. I can't write a loop that gets me every real number. Okay? Or that even would get there if I gave it forever. Okay? So for the loops, I could write a loop that would eventually get to any arbitrary natural rational number, right? I could write a loop and eventually I would get to 5 over 1,000, right? It's way down here somewhere. But eventually I would hit it, okay? Here, I've even said more. I've said that for the real numbers, I can't do this. There's no way to list them. There's no way to enumerate over all the real numbers. They're bigger. Okay? And this is one of those first I can't do things theorems. Okay? This is this is the first real one that says there's limitations on anything we want to do with a computer. Right? A computer cannot list all of these numbers. I can't run a routine over the real numbers. There are things that are bigger than the natural numbers in a very true sense. Are there any other questions? This is weird. Don't get me wrong. This is one of those weird things. Okay? But this idea, assume otherwise. Assume that I could list them, and then you found out with a number that you can't list. Is weird. Okay. 1 to 5. How do we feel about this? Yes, because we've proven that you can't. So the question is, if someone figures out how to list all the real numbers, will math implode? Yes, because then we've got an inherent contradiction in our logic. And, we have to go back to the drawing board. Which has happened twice. Twice we have had to go back to the drawing board. It's not that we can't count them because there are too many. Okay? And, Michael is over there trying to defend the axioms, right? That would never happen, right? Well, Gödel's incompleteness theorem says we don't actually know. Okay? Now, we're pretty confident in this one, right? But there do exist statements that we can't prove that our logic is consistent. That is Gödel's incompleteness theorem. But Michael is sitting there holding the line, so we want him to hold the line. I'm the one going, it's all castles built in sand. We're fairly confident that won't happen. This is the cardinality, the size of this thing. And we call that cardinality Aleph 1. But again, I said you don't need to know this. You only need to know that this is a bigger thing than these things. These things are all countable. The rationals, the integers, the even integers, the natural numbers, these are all countable things. This is another order of big. Okay, that's the point, is that this is another order of bigness. I can't enumerate. I can enumerate over these sets if I give myself the years of the universe. I can't enumerate over that set. Okay. All right. I see other questions, things like for repeating things, like the fact that 0.99 equals 1. I will be happy to answer those in chat, but this is the last of the... I'm now out of time on my stream. It is now 4:46. I've run a minute over. So if you want to ask me that, I'll hang around for another 10 or 15 minutes, and we can prove that African swallows could hold the coconut, but not European swallows. So, but but remember that African swallows are non-migratory. So it's kind of a purposeless thing, right? An African swallow is not going to bring a coconut to Northern Europe. Any other questions? Those are deep, important questions. Okay. I am going to then sign off, and I will be in Discord chat if you want to speak to me. Thank you.